So I'm going to talk about two things today. First, I'm going to talk about a framework for how to compute gradients of expectations in general. So you might have heard a lot of people in the earlier lectures talking about estimating gradients of this or that. So that's something that's pretty much all over the place in machine learning, but especially in reinforcement learning, where it's a little more complicated to compute the gradients you need. So I'm going to talk about a general framework that lets you mechanically calculate whatever gradient you need without having to think about it. Then I'm going to talk about a different class of policy gradient methods than the ones we've been hearing about so far, where instead of instead of trying to change the probability of your actions, or instead of writing down a loss function that looks like probability of actions times advantage, you have a value function that tells you how you should adjust your action, in which direction you should adjust your action to make it better. So instead of considering how the probabilities of different paths change by adjusting your policy, you look at how the paths themselves would change, which is why it's called a pathwise derivative method. Okay, so what are we doing in machine learning? A lot of the time we're estimating gradients. We're getting noisy estimates of gradients, and then we're going in the gradient direction. And if you do that for long enough, you get to a good solution. So one thing that drives a lot of the innovation in deep learning is the fact that backpropagation is something you don't have to think about. So you don't have to, maybe in the old days, you would have to think about your loss function and your architecture and then take out a notebook and calculate how you're going to compute the gradient of your loss function and how you're going to algorithmically, how you're going to do this with, like, how you're going to actually do the algorithm to calculate this gradient. So you would have to write down a bunch of, you would have to do a bunch of math every time you wanted to come up with a new kind of architecture. And now all you have to do is figure out how you're going to compute your loss function. And there's this nice algorithm called backpropagation, which will compute your gradient as efficiently as possible, and it's guaranteed to be correct. And you don't even have to think about it because libraries like Chainer and TensorFlow will do it for you. So that gives us a lot of freedom to think about other things. However, backprop doesn't tell you exactly what you're going to do in the setting of reinforcement learning, or with some other probabilistic models, you have components that you can't just backpropagate through. And there are two reasons why you might not be able to backpropagate through them. One is that the component is non-differentiable. So, well, that might mean that your loss function itself is non-differentiable. So you're not going to, so it's not that, I mean, you're going to magically make it differentiable by computing the gradient in some other way, but you might, but often if you have some non-differentiable thing you need to put in your loss function, you can also make it so the loss function is differentiable, and then you do have, you can use gradient descent on it. So I'll talk about an example of that later, hard attention in particular. And another reason is that there are components in the loss function you want to write down. There are components where you don't have full access to this component. You don't know what the function is. So in reinforcement learning, you assume that the agent is known. So you know exactly what the functional form of the agent is. You have some kind of neural network and loss function which you can differentiate through. But you don't have access to the environment. The environment is an unknown thing that you can only access by interacting with it. So you need some other way to estimate gradients that doesn't involve actually like analytically writing down your loss function and differentiating that. So anyway, that's why the gradient estimation problem becomes non-trivial in reinforcement learning and in other certain kinds of probabilistic models. So we've seen two basic kinds of gradient estimation in various places. One is we have, in the case where you actually can write down your loss function and you have access to the full functional form of it, then you can just do the backpropagation algorithm. And the other case is we've seen policy gradient methods where we have what's called the reinforced kind of estimator, where you have log probability times sum of rewards. But actually, in a lot of places, it's not just one of those two ideas that you can use without any thought. Often, you have to do some kind of combination of those two ideas. So, for example, let's say you have your policy is a recurrent neural network. So that would, let's say you have. Let's say you have probability of action given a hidden state of an RNN, because you don't actually see the full state at every time step. You only see an observation at every time step. So then you're going to have some kind of update equation for the hidden state of the RNN. So this is just saying the hidden state at time t equals some function of the hidden state at time t minus 1, the action at time t minus 1, and the new observation at time t. So we have some kind of update equation, and then our action depends on that hidden state. Okay, so if we have something like this, then we're going to have to do some kind of backpropagation through time to to figure out how the RNN hidden state is going to depend on the parameters. But then we're also using a reinforced style estimator to see how, to look at the action probability and how that's going to affect the rewards. So this involves some combination of our two kinds of techniques. Another possibility is instead of having a reward function, which is just some random quantity that the environment gives you and you have no idea, well, the environment is kind of a black box that just spits out a reward at every time step. Sometimes there's a little bit more known structure to the problem that we can exploit. So sometimes our reward is some known differentiable function. For example, let's say we're trying to learn a classifier, but we have what's called a hard attention model, meaning that the model is making a decision of what to look at. Then this decision of what to look at is not something you can differentiate through, at least in the hard attention models. I'll go into detail more later, but the point is that our objective is some particular function, which is the log probability, which we have access to, and we want to take grad log, we want to differentiate it, as opposed to just saying the reward is some function that we don't get to look inside. So this work was motivated by noticing that it seemed like a lot of papers were proposing models that had some combination of these two estimation techniques, but they would all do their own convoluted derivation of their gradient estimator. And often they would all use different ways to derive these things, and it was just kind of annoying reading it for every new paper. So we figured that we should write down some kind of general framework. Okay, so first let's just talk about gradients of expectations a little bit more formally, and I'll talk a little bit more formally about what I was alluding to in the last slide regarding two different kinds of flavors of gradient estimation. So in general, gradient estimation means we have some expectation. Here we have expectation of capital F. And here capital F is some random variable that has a scalar value. And there's a bunch of complicated stuff that happens to give us F. So F could be some kind of log loss, or it could be a reward, and so on. And then we have some parameters that we're trying to optimize. And we're going to call those parameters theta. So then the next thing, the important question, which will determine what kind of estimator we need to use, is where is theta in this expectation? So when we write down the expression for this expectation, where does theta appear? So one possibility is that theta appears somewhere in the distribution that our random variables are sampled from. So that means we have parameterized distributions that we're sampling our random variables from. So here, x we have some random variable x, which is sampled from a distribution p of x given theta, and then we take f of x. So this is the kind of setting where we derive the reinforced estimators, which are used in policy gradients. And so here you get an estimator that looks like you take a sample of x, and then you take f of x times grad log probability. And it's called the score function estimator in general when we're not in reinforcement learning. Okay, the other possibility is that our random variable appears somewhere inside the expectation expression, but our distribution is totally fixed. Our distribution that we're calculating the expectation over is totally fixed. So in the second setting, we have some random variable z from a fixed distribution, like let's say it's a normal random variable with mean 0, standard deviation 1. And then we transform that, then we apply some function to our random variable, to z, and then this function also depends on theta. And then we take our loss function, f. So we have f of x of z comma theta. And then to compute the gradient of that, we just swap the derivative and the expectation. So here, to compute the gradient of this type of expectation expression, we just say that the gradient of the expectation equals the expectation of the gradient. Now, of course, this doesn't always work. So this only works under certain differentiability conditions. In particular, if the thing inside the expectation has to be, let's see, I think it has to be continuous. Does it have to be differentiable? I mean, it has to be almost everywhere differentiable, but if it's just continuous, then we're in good shape. But if it's discontinuous, then that means you have an infinite derivative somewhere and you're ignoring that because you're never going to see it. I'll talk about that in more detail if we have time, when these different estimators are going to work. So anyway, this one is called the pathwise derivative estimator. This is the one that you're probably more familiar with because this is what is used in most places in machine learning. So as one example of this, when you train neural networks with dropout, you have this random dropout mask that you're sampling for each update step. And this dropout mask is usually not parameterized in any way. You just say, I'm going to mask each activation with probability 0.5. And so that's like you have this random variable z from a fixed distribution that you're putting into your objective or into your computation. And then we can just, well, we care about the gradient of the expectation over dropout masks, but we can get an unbiased estimate of that gradient by just taking the expectation of the gradients. Okay, now I've been talking about this as if there are some problems where you can use one kind of gradient estimator and other problems where you can use the other estimator. But actually, I should be careful about that because which gradient estimator you can use is not actually a property of the problem itself, or it's not a property of the probability distributions involved. It's actually just a probability of how we're writing down our objective. So in pretty much any case, we can write it down. If we have a certain stochastic process, meaning if we have some kind of computation that gives us a loss value at the end, we can write it down in multiple different ways. And one way is going to allow us to do the pathwise derivative estimator, and the other way is going to allow us to do the score function estimator. Though actually, for certain kinds of losses, you can't really. You can always write down the you can always write down the loss in both ways, but you can't always differentiate it in both ways. It might be that only one of these forms allows you to get a gradient estimator. And this is often called reparameterization. So you might have heard of the reparameterization trick, which is where you take you take something that looks like it should require the score function estimator, and then you reparameterize everything so that you can use the pathwise derivative estimator. So actually, let me just give you like a really simple example of reparameterization. So let's say we have a Gaussian distribution. So we have x is from a normal distribution with mean, mu, standard deviation, sigma. So we could, and let's say our parameters, let's just say we're going to identify theta with, we're going to say that that's just defined to include mu and sigma. I haven't defined a loss function. I'm just saying this is some variable that appears in our computation. So here we've described x in terms of a parameterized probability distribution, but you could just as well say we're sampling z from normal 0, 1, and then we're just taking x equals mu plus, actually, I mean, we have to take some matrix times z, where this is a square root of sigma. So, and that'll give us the same distribution. So in this case, our random variable is from a fixed distribution, but then, and then we transform it in some, according to some deterministic function. Whereas here we have a parameterized distribution. And we didn't actually change what the distribution was. We just changed how we're writing it down. Okay, so what's a stochastic computation graph? It's a DAG, which stands for directed acyclic graph, where each node corresponds to a deterministic or stochastic operation, which depends on some previously computed nodes. So it's a way of describing some computation where you compute a bunch of things in succession. And what we're going to do here is we're going to show how to automatically derive unbiased gradient estimators where you have any loss function that's described by this kind of DAG. You can then write down an unbiased gradient estimator for this loss function. So on the left-hand side, this is an illustration of a normal computation graph. So computation graph just means a DAG where each node corresponds to some intermediate value in the computation. And then in this case, we're going to assume that there's a loss function at the end. And we're trying to compute the derivative of that loss function with respect to some parameters, which are earlier nodes in the graph. So in a normal computation graph, we can do the backpropagation algorithm to compute the gradient of the loss with respect to some parameters. But with stochastic computation graphs, we need to do something a little different, because we have some kind of stochastic node in the graph where this node is no longer a deterministic function of its parents. It's some random variable that is conditioned on its parents. Mm-hmm. Yeah. So the question was, neural networks with dropout is a stochastic computation graph. Yes, I agree. So actually, let me show as an example what the stochastic computation graph would look like for neural nets with dropout. But I'll do that on the next slide when I get to some examples. Okay, so first example is hard attention. So this is a very simplified model of hard attention relative to what people actually use, but it's enough to illustrate the main point. Let's say, so this is just an example of why it's going to be somewhat non-trivial to compute the gradient estimator for some kind of loss function we might want to define. So let's say we look at the processes as follows. This is the model we want to write down. You look at the image, which is called observation 1. Then we determine some kind of crop window, and our action is this choice of the crop window. Then we get the cropped image called observation 2. And then, then we output our guess of what the label is for the image. So we have some kind of neural network that takes the cropped image and it guesses the label. And we give it a reward for getting the right label. Okay, but now there are two versions. There are two ways of doing this that are reasonable. Two ways of actually defining this loss function about getting the correct label. So version 1 is your network outputs some label, and then after you output the label, you get a reward of 1 if it's correct and 0 if it's wrong. So if we were to draw so I'm going to draw a graph, and hopefully it'll, I haven't explained all the notation yet, but hopefully it will sort of make sense. So theta is the parameters that we're trying to learn, which determine not only, it determines your choice of crop window and also the classification decision. So theta is going to control two things here. But this is just all of our parameters. So first, as a function of the first image and our parameters, we determine the crop window A. Then that in turn determines the second observation, which is the cropped image. Then the label guess, called Y, is a function of our model and also the cropped image. And then after we've decided on our label guess, we're going to determine, then there's a reward, which is 1 if it's correct and 0 if it's wrong. Okay, that's a reasonable way to do this, but actually when you think about it, you realize we're actually throwing some information away there. So if we just sample from this model and we get the wrong label, then we're not using the information we have, which is what the correct label is. So let's say there's 1 million labels. Like let's say this is maybe not 1 million. Let's say we have 1,000 labels, as people often do in these image classification problems like for ImageNet. So then if you start off with a model that's getting the label wrong most of the time, then you only get the information about the correct label when you happen to guess the right one. So you only get it about 1,000th of the time at the beginning. Whereas you actually, I mean, when we set up this loss function, we as the experimenters know what the correct label is, so we should be able to use that information in training. So that suggests a more, that should suggest another way of defining this loss function, which is okay, it's just a change that we're going to make at the end. So instead of outputting our label guess, we output some parameter that specifies our probability distribution over labels. So it might say 0.9 probability of cat and 0.05 of dog and so on. And then the log probability, then we have the log probability as our objective, which is a function of this probability vector. Or we could just say, instead of log probability, just the normal probability. So the probability of the correct label. Question?
So, but in a way, when you get the softmax loss, isn't that what we do? We get probability in the different classes. I'm just trying to understand.
Oh yeah, the question is if we take the softmax loss, don't we get probabilities anyway? I'm just saying these are different ways of specifying of just writing down our loss function, which are going to give us different gradient estimators. So actually, I haven't described what the gradient estimators are yet, so maybe that'll clarify the answer. So if we wrote down this model, then it would make the most sense to do a reinforced style estimator on both the action, which is the crop window, and the label. So we would have, so the gradient estimator for this model, just using reinforced, would look like grad probability of action times the reward plus grad log probability of label times reward. So that's, okay, that's all well and good, but this is a kind of high variance estimator because we're not using the information about the correct label. Whereas in this model, we're in effect integrating out the choice, well, our sampling of the label. So it's a lower variance estimator. And here we can, well, we want to write down a loss function. Here what we're going to write down is a loss function that looks like grad log probability of action times reward, which in this case is the log prob, plus a term where we directly backpropagate from the log probability through this probability vector to the parameters. So we also have a path that we can directly backpropagate through. So I'll actually write down what our loss function is in this case. Okay, so it turns out that the gradient estimator for this model on the right is we have grad log probability of our action given the observation and the parameter times the reward, which actually let me just call it R, but this R equals log probability of our correct label given our model parameter and second observation. So that's the reinforced term that helps us update the crop window. But then we have another term that just looks like our log probability of y given theta and our second observation. So actually, let me put a little hat on this. I'm going to use the hat notation later, but the reason I'm putting a hat on it is we're treating this as a constant when we compute our derivative, but we're not treating this thing as a constant. So, I mean, sorry, I have also grad theta here. So we have two terms in our gradient estimator. One is a reinforced type term, which is like grad log probability times reward, which is treated as a constant. And the second term is our grad log probability of the of our loss, where we actually differentiate through all the deterministic dependencies. So we backpropagate through kappa and back to theta, like back through our neural network that outputs kappa. Yeah. Uh-huh. Yeah. Okay, yeah, so, yeah, that's true. So it's probably a deterministic function, so we could write it as a square. Though in this case, we're not actually differentiating through this dependency anyway, though we could make it deterministic and differentiate through this. It's also, we could make it random though also. We could say we're cropping, yeah, I don't want to get too much into the detail of that, but you're right. So the question was, shouldn't O2 be a deterministic function of the previous observation in the crop window? Yeah, that's true. Yeah. Mm-hmm. Okay, the question is, if O2 is a deterministic function of its predecessors, then can we actually get a better gradient estimator, even if y is also stochastic? It depends. We might be able to write down there are often going to be many different estimators we can write down, and yeah, so we often have many different choices, and we might be able to get a better estimator, but we might get a worse estimator also if we try to use that information, because we might have a really non-smooth derivative for a certain dependence. Actually, let me get more, I'll talk about some of these issues about which estimator is better later. Yeah. Okay, let me also give an abstract kind of example where this is just designed to illustrate all the different kinds of different kinds of motifs that we have to deal with, or that we want our general framework to deal with. So here I've actually done something slightly different, and I've used diamonds to indicate the nodes that are part of our loss function. So that's, I mean, here it's assumed that the costs are just, I mean, the costs are deterministic functions of their predecessors, and in this figure I happen to use diamonds to indicate the deterministic nodes that are also being considered as losses. But here, anyway, we're defining our loss function as C plus E, and we also have a stochastic node called B, which is, okay, there's some probability distribution, P of B given A and D. And then we have two we have two parameters. We have theta and phi. Okay, so we want to be able to compute the gradient of the loss, of the expected loss with respect to theta and phi. And we want to do this in one nice quick calculation. The way backprop would be able to do that if these were all deterministic nodes. So I'll just tell you what the result is. We have, so we can construct what's called a surrogate loss, where we add in a bunch of terms to the surrogate loss, where we treat the stochastic node as a constant, and we introduce terms of the form log probability times future cost minus some optional baseline, which is like the baseline we've been seeing in policy gradient methods, which doesn't affect, which only helps with variance reduction, but doesn't affect the mean of our gradient estimator. So anyway, we write down a surrogate that looks like C plus E plus log probability of our random variable B, given its parents, given all of its predecessors, times the future costs, which are treated as a constant. So in this case, what you have to include, what you have to multiply the log probability by is all of the costs that are descendants of the node you're looking at. So whenever there's a path from B to some cost node, you include that, but you don't have to include E. You don't have to include E in this this loss that we're multiplying by log probability. That's sort of the non-trivial thing here as compared to the attention model from the last slide. When you have these terms like log probability times future costs, you don't have to include things that are not dependent on the node that we're looking at. So anyway, we write down this surrogate, and then then we just have to differentiate this surrogate loss, and we get an unbiased gradient estimator. And so basically, this has two different. This includes two different kinds of terms. One kind of term tells you how the parameters affect the cost through a chain of deterministic dependencies. So, like for example, you'll see that there's a path through a chain of deterministic nodes that goes from phi to E. So that's one source of dependence. But then we also have a chain of dependence that goes from our parameters to a probability distribution, which will then affect the losses because we're just changing the probability of some node, and then that changes the losses that come later. So we also have these dependencies where our parameters are affecting distributions. So in summary, we have parameters directly affecting the loss, and we also have parameters affecting distributions. So we get two kinds of terms. There's a question? Oh, phi. Oh, that should say, I mixed up psi and phi, so that should be phi. Mm-hmm. Oh yeah, the question is, like if we have a deterministic node, if we have other deterministic nodes between our stochastic node and the cost, what do we do with those? So do we include those in the list of descendants? So the answer is every loss term that is a descendant in the DAG of our stochastic node, we have to include in the expression multiplying log probability. And this includes edges that are going to stochastic nodes and deterministic nodes. So if there's any chain of edges that leads to the cost from the stochastic node downstream to that cost node, then we have to include it in the term multiplying the log probability. So anyway, I'm not expecting this to be like 100% clear. Well, actually, you can. We have a paper called Gradient Estimation using stochastic computation graphs. So in the paper we sort of lay out all the notation really carefully, and then we provide a couple theorems that say what the general expressions are for the gradient estimator. So if you want more detail on it, you can check out the paper. But anyway, just as a preview of the results, we show that there's a general method for calculating the gradient estimator of a general stochastic computation graph. So there are two versions of this. One version is what I've been describing previously because it's what you actually do in practice, which is called the surrogate loss version. And the idea is that you're going to construct some kind of loss function where when you differentiate it, you're going to get your gradient estimator. And what the surrogate loss looks like is you have a bunch of expressions of the form log probability of your node value times the sum of downstream costs, which you treat as constants. So here, this is the part that comes from how the parameters affect distributions. Like this is just accounting for the fact that your parameters are going to affect the distributions of random variables in the graph. And then you also have a bunch of terms where you treat your costs as variables that depend on all your parameters, but you treat all the other random variables as being constant, as being frozen. I mean, you treat all the you treat all the stochastic nodes as being constant in those terms. So these are like this is like in dropout. You treat your dropout mask as a constant, but then you differentiate through everything else. So that's one way of thinking about this kind of gradient estimation. The other way is we can define a kind of back propagation algorithm that generalizes the usual backprop algorithm by adding in some new operation that you do when you hit stochastic nodes. So the normal backprop algorithm you can see as dealing with the special case of a fully deterministic computation graph. And so if you run the normal backprop algorithm, then you just need to do something special when you hit one of these stochastic nodes. So the normal backprop algorithm is based on doing what's called a topological sort of all the nodes in the graph. So you walk through the nodes starting at the end and going towards the beginning. And at each node, you have grad loss with respect to that node, and you push that gradient back, and you increment the gradient at all the previous nodes by saying, yeah, so you update all the predecessors nodes gradient backprop result. So with the stochastic computation graph, you do a similar algorithm involving a topological sort, but you just have to do something different at a stochastic node where you just backpropagate log probability times sum of future or sum of descendant costs, as opposed to taking your gradient and multiplying it by a Jacobian, like you do in the normal backprop. Yeah, question? Oh, yeah, yes, yeah. Future costs here just means downstream costs, yeah. So, right, in the reinforcement learning setting, we have like everything, we have one reward at each time step, so we just talk about sum of future rewards. But in general, you might have a graph where it's only a partially ordered graph. So you might have different branches of it with different kinds of rewards on it, on different branches. So then you only need to include the downstream rewards as opposed to all of the rewards in, well, there's no sense of future or past, right? Okay, so let's see, let me just give a few more examples to illustrate this idea. Okay. Let's see, what did I do with my chalk? Oh, here it is. Okay, so what does dropout look like? Well, let's say we have our input to the network where we have our image and Then we have, let's just say we have one weight matrix. Okay, the image is an input and the weight matrix is an input. So then we have the output of the, actually let me just call this x for the image, and it doesn't need to be an image, it could be just a vector. So we compute, let's say we compute y equals wx, so we have some kind of linear layer, and then actually, this is just going to be logistic regression. So then we just have some kind of, we have a correct label. Well, we have some kind of label. Let's call it label true. And we have some kind of log loss. So this is just like log probability of, I mean, this would usually mean we're applying the softmax to our vector of activations, and then we take the log of the softmax and then index it at the correct label. So this is what our normal neural net is going to look like. And okay, this is, oh, let's see. Our parameters are, so W is our parameter vector that we're trying to differentiate with respect to. Y is a deterministic node, and the log loss is a deterministic node. And everything else is just an input. So then if we add dropout, that would mean we, that means we're well, I guess this is a stupid place to use dropout because we only have one layer. So this would be pretty bad. So let's actually add another layer. So let's say we have, this is W2. So we also have some intermediate result, which we're going to call H. And we have W1 going into H, and X goes into that. Okay, so here's our new graph. So then with dropout, we're going to take H equals W1X. And then we multiply that by some kind of dropout mask, which is random. So then we actually have another input here, which we're going to call Z. And Z is from some fixed distribution, is just like a vector of Bernoulli random variables, which is not parameterized in any way. So this is what it would look like for a normal neural network. Actually, I'll also draw what it looks like for what the stochastic computation graph looks like for policy gradient methods. And actually, this will illustrate a useful point. So we have our states. This is just for an MDP, so we're not going to have partial observations or anything. We have our states, and then we're going to have our policy parameter theta. And then the actions depend on the states and our policy. So here, the states are all stochastic because we have some kind of transitions, stochastic state transitions. And we have our stochastic actions. And the action depends on the current state and also the policy parameter. And the action, also the next state depends on the action. So this is just saying that we have like probability of ST plus 1 given ST AT. That's what we have at all the states, and then we also have some probability pi sub theta of action T given state T. Actually, let me put the theta in the argument instead of the subscript. So this is what the stochastic computation graph looks like for policy gradient methods. And then we have a reward. Let's just say for simplicity that the reward is only at the end, just to reduce clutter. So this is just, let's say this is just some deterministic function of the state. Well, our gradient estimator looks like sum over t equals 1 to 3 of grad theta log probability of action t given state t, comma theta times reward, right? This is just a reinforced estimator. So note that even though reward was a deterministic function of the state in this particular case, well, it's not always in reinforcement learning, but let's say it is, that doesn't even help us because we're not actually differentiating through this dependence when we use the reinforced estimator. So one thing people sometimes wonder about is what if we reparameterize this computation graph? So, I mean, we've been looking at continuous control problems a lot, like these robotics control problems where you have some action that's from a Gaussian distribution. So why don't we reparameterize it so, so now this graph looks like state 1, and we sample like some random variable z from a normal distribution with mean 0, standard deviation 1. And then we deterministically, we make the action a deterministic function of that. And then, so then our graph looks like this. And we have our, of course, our policy and so on. I'm not going to draw the whole graph. Let me erase the other stuff. Okay, so yeah, why don't we reparameterize the computation graph to look like this instead of looking like S1, A1, like this. And this just means we have like action equals pi of S z theta, where z is some random noise. Okay, so we can do this perfectly well, but actually we run into a little problem, which is then we end up having to, okay, if we actually write down the gradient estimator for this, we notice that we have some term that's like probability of S2 given A1 and S1, or let me just write it as S1, A1. But now A1 depends on theta, so if we were to go and try to compute our policy gradient estimator using this version of the computation graph, we would end up having to differentiate. Okay, we would end up with a loss term that's like probability of S2 given S1 and A1, where A1 actually depends on theta as well as S1 and random variables. So we would, oh, and we have this is times reward. So we would end up with something like this, because we have to look at how the parameter theta affects the probability of S2, because there's a deterministic chain of dependencies going from theta to S2. Okay, I mean, we haven't seen the problem yet, but what if we don't, I mean, in reinforcement learning, we usually don't assume we know the model of the system. So P is something that we don't have access to. The transition model we don't have access to. So now we're in trouble because we have some term in our gradient estimator that we don't actually have access to. So we can't use this form to actually compute a policy gradient unless we have the dynamics model. If we do have the dynamics model, then we can go ahead with this, and this is great. Well, it might be a bad estimator, but in principle, it could give us a correct estimator. On the other hand, so why didn't we run into this problem before with the normal policy gradient, where we run into the fact that the dynamics model is unknown? Why didn't this cause a problem? Well, the problem is, well, here the dependence on theta was blocked by a stochastic node. So the way you can look at it is you have your parameters, and you have some kind of dependence. You have the dependence on these parameters flowing outwards through deterministic nodes, and it gets blocked whenever it hits the stochastic node. So you can imagine like what happens when you wiggle the parameters. How is that going to affect the loss? If you wiggle the parameter, well, it hits the stochastic node and then it gets blocked, and then you don't have to worry about this dependence anymore, except through reinforced type terms that come from the grad log probability. Whereas in this term, we wiggle the parameter, and then it propagates through the action, and then it goes into the probability of the state. And, but the problem is we don't know this. There's a function here. This node is computed by a function that we don't have access to, so we're in trouble. So that's kind of an intuitive overview of the issue. So anyway, this gives you this framework gives you an unbiased, a way of deriving an unbiased gradient estimator, and it also tells you a general way of figuring out what you should put in your baseline. So you can derive a generalized version of the idea of a baseline, where it just depends on the structure, where the question is, what variables am I allowed to put in my baseline? Like, what variables can the baseline depend on? And the answer is you just have to look at the nodes that are downstream from your stochastic node. So anyway, this matches up with what people have derived in many previous works, but at least here it's in a more generic framework.
Question?
Uh-huh.
The explanation you gave for blocking,
Uh-huh.
which graph was it? Is the one behind you?
Uh-huh.
Which one is blocking, which one is not blocking?
Oh yeah. Yeah. Let me draw out the full graph. Okay. I'll draw like a example that's sort of a minimal working example. So here's the graph on the right. Here's the graph. This graph on the left has this is like a reparameterized policy gradient, and the graph on the right is without reparameterization. And these correspond to the exact same expectation of reward given parameters. So we have some kind of expectation of R given theta, where we're taking the expectation over all the intermediate stochastic nodes. And both of these graphs have the exact same expectation. So this is just two ways of writing it down, which are going to allow us to mechanically derive different gradient estimators. Okay, but the blocking referred to this one. In this one, the dependence of R on theta was blocked by the stochastic node. Well, actually, the main issue is the dependence of, the particular point I was making was that the dependence of S2, the probability of S2, given its predecessors, this probability distribution was, the dependence of this distribution on theta was blocked. So it was blocked by the stochastic node. So for example, let me actually just show you what the gradient estimator looks like for this graph. Oh, by the way, so I should mention that you can already derive these gradient estimators using what you already know from calculus. All you have to do is write it down as an integral. So you just write down your expectation as an integral, and then you go and compute all the terms in this integral. But that involves a bunch of calculations. So the whole point of this is to derive something that allows you to skip the integral. Okay. So what does the gradient look like here? So we have. So we have to look at, so first of all, we have the reward treated as a variable. So let me just write this as R, which implicitly depends on theta. So I'll write R of theta to indicate that we're treating as a variable that depends on theta, but where we treat all the stochastic nodes as fixed. So this is like the pathwise derivative kind of term, and then we also have. Actually, let me just say that this is. Okay, let me just leave it like this for now. So we have this is our pathwise derivative term, and then we also have we have our grad log probability terms. So we have log probability of S1. Well, okay, this term, this is just like the initial state, so this doesn't depend on anything, times reward, which we're going to treat as constant, plus log probability of S2 given S1 and A1 times reward, which we're treating as a constant. And then we want to differentiate this with respect to theta. So this term this term ends up being 0 because we're treating all of the stochastic nodes as constants when we compute that term. So this term doesn't depend on theta, it just depends on S2. So this goes away. This term doesn't have any dependence on theta because we're treating S1 as a constant and we're treating the reward as a constant. And then this term, okay, this term actually we do have to worry about because the action depends on, the action does depend on theta. So, so this term will have, we have a gradient from this term. So it looks like, I mean, we can expand it into Jacobians, but that's not terribly useful. So anyway, this gives us some term, and we need to know this function to be able to compute that term. So then we're in trouble, unless we have access to this function. And recall that A1 is some deterministic function. It's some function of the form pi of S1 theta and z. So that's why when we this thing depends on theta. All right. Well, I'm mostly out of time, but I can answer a few questions. Hi. Yeah, that's right. So just to repeat the question, it was, I mean, we did this reparameterization, but we ended up with something that's worse than what we started off with. Is that, so that, yeah, what exactly is the question?
Well, I guess, I want to check my own understanding if that's what happened, like the left-hand graph would not work in like the surrogate loss framework,
Mm-hmm.
and then we have to stick with the right-hand graph, is that?
Oh yeah, so the way I would clarify it is to say there are many different ways of writing down the stochastic computation graph to describe a particular kind of loss function. Like this is the thing we're trying to optimize, and we have a lot of leeway in how to write down all the intermediate steps that lead up to getting this reward. And we're not actually changing the objective, we're just changing how we write it down in a particular notation. It's like you can write down x plus 1 parentheses squared, or you can write down x squared plus 2x plus 1. This is the same algebraic expression, but we're just writing it down in two different ways. But these two different expressions might, then if we have some kind of algorithm that takes in an expression, that algorithm might do different things to those two different expressions. So here, it's like we have two different equivalent expressions for the same mathematical object, and then we have an algorithm which is this surrogate loss, this procedure for computing a gradient estimator, and this might do something invalid when we write it down in one way, when we write down the loss in one way, but it might be valid if we do it the other way. And here valid is, the reason it's valid in one case and not in the other is because in there's certain functions in our graph that we don't actually have access to. And if we write down the loss in one way, we end up with terms that involve those functions. And if we write it down the other way, we don't have those terms. Mm-hmm. Oh, yeah, I should have shown that when I did dropout. So, yeah, we could also do dropout with the score function estimator. So we can say that our activation, let's say we have our activation vector h. We can say that's some random variable that depends on our noise and also it depends on the weights and the previous layer. So we can write it down like this, and then we have grad log probability of the activations. Yeah, we have a term that involves grad log prob, as opposed to back propagating through the network. And actually, it sounds kind of silly, but there have been times when people. So you might have heard of Bayesian neural networks. So the original version of Bayesian neural networks just used the score function gradient estimator. So I think it's an 80s paper by Hinton where he described Bayesian neural nets using the score function gradient estimator. And then later, people figured out that you can do the reparameterization trick on it and get the same thing with much lower variance. Oh, for the policy gradient case? Oh yeah, so then it's going to be, it's just going to be like grad log probability of action 1 given S1 theta times reward hat. Oh yeah, and then we have other terms that end up being 0 as well. Okay, yeah, so we also had, well, we have to consider some term R of theta, and let's see, and then we also, for every stochastic node, we have to add a term to the loss, but they all end up being 0. So we have like log probability of, we also have a log probability of S1 times reward hat, and log probability of S2 given S1 A1. But note that we're treating, like for the S2 term, we're treating the predecessors as being frozen in these, as being constant. So we don't end up getting a gradient from those terms. Yeah. So the reason I sort of described what the algorithm looks like mechanically, where you have a bunch of terms where you treat some things as constants, and then that gives you your surrogate loss. So I didn't derive it, and what happens is you can just derive it using pretty straightforward calculus by just writing down the expectations as integrals and doing some straightforward calculations. I don't think it's particularly illuminating to go through these calculations, so you can either do them yourself as an exercise or find them in the paper. And anyway, you end up with this. You end up with this kind of this result. Yeah. And this has also been used in. So people have added something to PyTorch that uses this framework to deal with random variables in PyTorch. So it's something that can nicely be integrated into these kind of autodiff frameworks. Yeah. I don't know. Yeah, I just heard of it. I don't know if it's like in the PyTorch distribution or if it's some library someone wrote. Yeah. Question? Oh, yeah. So the question is, what are the conditions for using the pathwise derivative? I think I have a couple minutes, so let me just actually show you a pretty illuminating example of when the pathwise derivative can go wrong. So let's say we have a function f of x, which is the step function. Here's x, and f of x looks like this, right? And let's say we're taking x is some normal distribution. Let's just say it's normal with theta as the mean and 1 as the standard deviation. Well, actually, let me say theta is sampled according to this distribution. So that means we have some kind of Gaussian. If we can draw the PDF for x, and it's going to look like this, right? And then we want to compute grad with respect to theta of expectation of f of x. Where here, note that we have p of x given theta. So theta appears in the distribution here. OK, so we can do our score function estimator, and that's going to work perfectly well. So then we get grad log p of x given theta times f of x, right? So this is perfectly good. Then let's say we try to reparameterize it. So we say z is from normal 0, 1, and x equals theta plus z. So this is score function looks like this, and pathwise derivative looks like this. So we reparameterize it, and now so we have now we just write it like grad theta of expectation over z of f of theta plus z, right? So now the problem is, OK, let's say we swap the derivative and the expectation. So now we have grad f of, so then we end up with some term, I'll say question mark equals expectation over z of so grad theta of f of theta plus z. OK, but f of x has derivative 0 everywhere. So now we just computed that this derivative is 0. So this is obviously wrong, and the derivative is not actually 0. So the problem here is that we had a function that was a discontinuous. It was a discontinuous function of its parents. So here f, we draw the stochastic computation graph, so we get x is a function of well, in the original graph, we had x is some stochastic node that depends on theta, and then f is a function of x. So the problem is that f is a discontinuous function. So so this reparameterization is OK. Well, I don't want to talk about the stochastic computation graph version of this, but the point is that you actually can't swap the expectation and the gradient when the function inside the expectation is a non-differentiable function of the thing you're differentiating with respect to. I mean, sorry, discontinuous. If you can't swap it if the thing inside the expectation is a discontinuous function of the variable you're differentiating with respect to. Actually, if it's non-differentiable, that's fine. So if you have a ReLU or something, then if this is a ReLU instead of a step function, then you're totally fine. And this, you're going to get a nice unbiased estimator. But if it's a step function, it's bad. And the reason it's bad is, imagine that we we change it from a step function to just a really, really steep function. Then our estimator becomes valid. But what it looks like is most of the time we get a 0. So it's a really steep function like this. So most of the time we're getting 0 gradient, but a small fraction of the time we're getting a really big gradient. So we have a really high variance gradient estimator in that case, but it's still unbiased. But the problem is when we make it actually a step function, then we never see the non-zero derivative because we never hit that step part. So that's why we end up with a biased estimator. And this is also an important example because it illustrates in what cases the reparameterization is a bad idea, even when it does work. So reparameterization makes things worse if one of the functions that you end up having to differentiate through is really non-smooth. So like when you reparameterize the graph, you're going to get new derivative terms in your gradient estimator. And if you happen to add in a term that involves a really steep slope, then, or involves some really rough function that has, let's say we have lots of wiggles in our function, then you're going to get a really high variance gradient estimator. So that's when you don't want to do it. And that actually, I think this does happen in practice in the kind of optimal control setting where you're differentiating through dynamics because often your dynamics are non-smooth. All right, I'm out of time. Thanks for your attention.